In Part 1, we'll look at the various causes of corrosion, some of the more common electrolytes, and the types of corrosion you will typically see while maintaining your aircraft. Corrosion is a natural phenomenon. It attacks refined metals and alloys in an effort to return them to their original state. Corrosion can be thought of as an electrochemical process because a small amount of electrical current is also generated as the metals corrode. Four conditions must always exist before corrosion can develop. There must be a metal that will corrode readily, called the anode. A different metal which has less tendency to corrode, called the cathode. An electrical path between the anode and the cathode, usually through metal-to-metal contact, and a conductive liquid called the electrolyte. A typical corrosion cell example that exists on your aircraft could have the aluminum skin as the anode, a steel fastener as the cathode, metal-to-metal contact as the electrical path, and rainwater, which may enter the small crevice between the skin and the fastener, as the electrolyte. Electrical current flows from the cathode to the anode through the electrical path, which, and here is the key, causes the loss of metal in the anode. Corrosion is like a cancer to an aircraft. Once it gets started, it will continue to spread without some preventive or corrective action. But remember, eliminating any one of the four conditions, anode, cathode, electrical path, or electrolyte, will stop or prevent corrosion. On the job, you need to know how different metals react with each other so you can spot potential trouble aboard your aircraft. The galvanic series chart, as shown here, shows how different metals compare with each other and how likely they are to corrode. The further apart two metals are on this chart, the faster one or the other will corrode if they are joined together. At the top of the chart are the metals which most easily corrode, such as magnesium and zinc. At the bottom are the metals which are the least likely to corrode, such as gold and platinum. Let's see how our example of the aluminum aircraft skin and stainless steel fastener looks on the galvanic series chart. Aluminum appears higher on the chart than stainless steel, which means that the aluminum will act as the anode and the stainless steel fastener as the cathode. This means that in a corrosive environment, there will be rapid corrosion of the aluminum skin where it contacts the stainless fasteners. On the other hand, if two metals are close to each other on the galvanic chart, corrosion will occur but not as quickly. Other factors will also increase the corrosion of a metal. One factor is the relative size of the anodic and cathodic areas involved. If the cathode is small compared to the anode, corrosion will be slow. If the surface area of the cathode is large and the anode small, the corrosion process will be accelerated and the smaller anode will deteriorate quickly. Another factor is temperature. As the temperature increases, resistance to current flow in the electrolyte decreases. So you usually find more corrosion in tropical areas than you do in cold areas. Corrosion also increases with the time the metal is exposed to a corrosive environment. Another very important factor is the type of electrolyte. Let's take a look at electrolytes in greater detail. Electrolytes are one of the four basic factors which cause metals to corrode. Any moisture from condensation, humidity, rain, or even coffee would function as the electrolyte. The most common electrolytes are water, acids, and alkalis. Water is by far the most common electrolyte. Its corrosive effects, however, depend on the chemicals in the water. Tap water is less corrosive than rainwater because rainwater has a lower pH level, which indicates a higher acid content. Salt water is even more corrosive than rain due to its high salt content, which makes it a stronger electrolyte. Moderately strong acids will severely corrode most alloys used in aircraft construction. By far, the most destructive is battery acid. In addition, sulfuric acid found in volcanic dust, ozone from electrical discharges, and even human and animal waste, which contain uric acid, are very corrosive to metals. At the other end of the pH scale, alkalis aren't generally as harsh as acids, but will still attack aluminum and magnesium alloys. Alkaline chemical cleaners are particularly corrosive to aluminum. This program will now look at the types of corrosion you will come into contact with while maintaining aircraft. We will use their most commonly accepted names in describing each type of corrosion. They are uniform, pitting, galvanic, concentration cell, intergranular, exfoliation, filiform, stress corrosion cracking, corrosion fatigue, and fretting. Uniform corrosion, as the name suggests, attacks the metal uniformly over the entire surface. Uniform corrosion is commonly referred to as rust on steel surfaces. If it is allowed to continue, uniform corrosion will cause significant strength and weight loss to the metal. Pitting corrosion is the most common form of corrosion found on aluminum and magnesium alloys, but can also occur in other alloys. Pitting corrosion generally appears first as small white or gray dots, and in its more advanced stages, a white or gray powdery substance, similar to baby powder. Galvanic corrosion results from two different metals being in contact with each other in the presence of an electrolyte, like our steel fasteners and aluminum skin. Concentration cell, or crevice corrosion, occurs in areas where two metals are joined and moisture works its way into the crevice and sets up a corrosion cell. Intergranular corrosion is one of the most serious types of corrosion and can be likened to cancer in a human being. Once it starts at an exposed grain boundary, intergranular corrosion follows a specific path and eats out everything in its way along the grain boundary. Because it occurs below the surface, it can go a long time without detection. Metals have a clearly defined grain boundary, which differs chemically from the metal within the grain center. The grain boundary and grain center can react with each other as anode and cathode when in contact with an electrolyte. Exfoliation corrosion is an advanced form of intergranular corrosion. The surface grains of a metal are lifted up by the force of expanding corrosion products occurring at the grain boundaries just below the surface. Filiform corrosion begins at breaks in the paint and is recognized by its worm-like traces beneath the paint surface, which can lead to intergranular corrosion. Stress corrosion cracking is caused by a combination of stress and corrosion. It is an intergranular cracking of the metal in a specific environment. Corrosion fatigue is similar to stress corrosion cracking, but is caused by the combined effects of cyclic stress and corrosion. The pressurization and depressurization of aircraft during flight is a prime cause of fatigue. Even small amounts of corrosion on fatigued parts lowers the fatigue stress limit. This will allow a fracture to occur at a point far below normal fatigue limits. Fretting occurs when two surfaces are highly loaded and vibration causes them to rub against each other. This causes their protective coatings to be worn away, exposing the unprotected metals to the environment. Fretting is often identified by black streaks at the surface interface. To summarize Part 1, we discussed the basic theory of corrosion. We discussed factors that influence corrosion, including various electrolytes. And we reviewed the major types of corrosion which affect aircraft metals. For some, this was a review. For others, it was brand new material. We should all now have a solid foundation of corrosion knowledge to move to Part 2, inspection requirements.